In today's lecture, we are going to continue our look at section 4. In particular, we're going to look at the method of Lagrange multipliers. It's a very powerful method. Very powerful method. And we'll do some problems and we'll look at why the method works. So firstly, let's actually outline the method first, and we'll do some examples, and right at the end we'll look at actually why it works. Now we know that much of applied science involves maximizing or minimizing functions where we have certain constraints, certain conditions. And this is where you can use, in many cases, the so-called method of Lagrange multipliers. So let's just look at the summarized version and see what we want to do. The aim... The aim or the problem is the following, okay? You want to maximize or minimize a function subject to some condition. So what I've written up there, the function that you want to maximize or minimize is just denoted by f. F might depend on 2 or 3 variables or more. And the condition or the constraint is denoted by this equation g equals 0. How do you do it? Well, in the previous lecture, we were looking at extreme values and things like this. All we were given was some function f, and calculate the extrema, classify the critical points, right? Here we've got an extra piece of information. We've got some sort of condition, some equation, g equals 0. So let's look at the method of Lagrange multipliers and sort of just get an outline for how it works. Suppose I have a function f and a function g. They're both differentiable. There's that condition again, differentiability. To find the local max and min values of f subject to the constraint g equals 0, basically what we want to do is find the values x, y, z and this number lambda that satisfy these equations. Now let's just look at that in a bit more detail. Remember, this nabla is just, this nabla f is just the gradient of f, and I've got the gradient of g over here, and I'm multiplying by this lambda. Now the lambda here is just a number known as a Lagrange multiplier. It's just a number, okay? So, you can either work with these equations and try to solve them. If f and g are functions of 3 variables, then how many equations will be here? Three, right? If f and g are functions of 2 variables, then you're going to get 2 equations out of this. Remember, this is a vector equation. So I've got a vector on the left and a vector on the right. Now, what I like to do is actually simplify the notation a bit. So I introduce a little bit of notation. I'm going to define the Lagrangian function, L, to be f minus lambda g. And the boxed equations, solving those is just equivalent to finding the critical points of this Lagrangian function, L. So you can either work with this and this, and then you've got 2 or 3 equations there and 1 equation there. Or essentially just differentiate partially with respect to x, y, z, and lambda and set them all equal to 0. Now, hopefully you can see already that we're going to have quite a lot of equations here. Now, if you want to be a bit technical and say, well, hang on, Chris, if you differentiate this L with respect to lambda, you get minus g, not g. But when you set it equal to 0, the minus sign disappears anyway. Okay? Okay. So probably the best way of showing you the method is just to do an example and really see how it works. We've got this Lagrangian, we want to find the critical points, we solve the resulting equations, and those points are going to lead to local max or min subject to the constraint equation, that g equals 0. So let me show you an example just for functions of two variables. Then we'll sort of expand our repertoire. Okay. Determine the maximum and minimum value of the following function that lie on this circle. So let's first of all geometrically think about what we've got. We've got a function f. What kind of function is f? What kind of surface will it lead to? What will it be? What's the surface associated with that f? A plane. Yeah, who said a plane? Yes, thank you. Okay, and what's the constraint equation? Well, it's just a circle, we're told. So this is our function, our constraint equation, just by rearranging this, is just this. So let's write down the Lagrange, calculate the critical points. F minus lambda g, where this lambda is just known as a Lagrange multiplier, it's just some number. Oh, for y. Yep, thank you. So given that f and g, let's just write it down. So what I'm going to do is just calculate dl dx, dl dy, set them equal to 0, and dl d lambda will equal 0 will give us the constraint equation. So we're going to solve the following. So go into here, take the partial derivatives with respect to x, and we set them equal to 0. So I'm going to get 3 minus 2 lambda x. So let's call that, I don't know, equation A. L sub y is going to be, we set that to 0, it's going to be 4 minus 2 lambda y. And of course, let's not forget about our constraint equation. So I'm just going to call that now. What we would like to do is solve A, B, and C for x and y, and possibly lambda. Okay, what you're really interested in is the x and y values. You're not really interested in the lambda values from a practical point of view. Sometimes it's nice to have them, and we will see really what they mean, but what you really want is the x and y values. Now, if you know lambda, you might be able to go back and use that information to get x and y. Okay, so it is handy to have lambda. So now we've got a bunch of simultaneous equations. Let's see if we can solve them. Well, I'm just going to rearrange this and make x the subject. I'm going to rearrange this and make y the subject. And then I'm going to plug x and y into C. So if I just make x the subject, I'll get that. If I make y the subject, so I'm going to get something like this. And then I'm going to take those two and plug them into my constraint equation. That's going to give me some value for lambda, which then I can use to get x and y. So these two then go into C, and we'll get, so now if I expand and clean this up, I'll get the following. I should get down to something like this, 25 on 4 lambda squared equals 1. So I can just rearrange that and get some values for my lambda. So, in this particular problem, we've got two values of lambda. We've got two Lagrange multipliers. Each of those multipliers can be used to get a point, an xy point. Okay? So let's sub so say lambda equals 5 on 2. I can put lambda in here, and I come up with a point. Okay, I can sub that in there, so I'm going to get 2 on 5 on 2, 4 on 5. Okay, so that's the case lambda equals 5 on 2. What about lambda equals minus 5 on 2? Well, they're going to lead to similar points. Okay, again, just sub in, you're going to get x equals the negative values of the point we just calculated. So, our points of interest are these 2 points here. Okay, so what do we do with those points? Well, let's put these points into our F and then compare the values. Okay, see if one leads to a maximum and one leads to a minimum. Let's just see. Just from the wording of the question, we would think that one will lead to a max and one will lead to a minimum, right? So let's actually just confirm that. Okay, so the value of f at my first point of interest, well, let's just plug that into our function up here. So I'm going to get something like 25 on 5, which is just 5. Okay, so for this one, I'm going to get negative 5. So now let's compare those two values. Which one's the larger value? Which one's a smaller value? Well, 5's the largest, minus 5's the smallest, so therefore we can make the following conclusions. If I let this circle be denoted by this curly C, then I can make the following. The maximum value of f on my circle is just 5, and the minimum value of f on my circle is minus 5. Okay, so that wasn't too hard, hopefully. I made sure I started off with a pretty simple example because, let me tell you, these problems can get very hard very quickly. Very hard. Anyone seen anything like this before? No? Okay. Let's look at the geometry of the solution. Here we've just drawn in the circle, so that's the constraint equation, or the curve associated with the constraint equation. And in this picture, at least, a few of the level curves of f on it. Now, let's go back to this particular equation here. This says that grad f is a multiple of grad g. Let's actually confirm that. So grad g. So these two vectors must be a multiple of each other, I guess, as long as the lambda is non-zero. Let's actually confirm this for our points of interest. At this point, if I draw in the vector grad f, now because f was this function here, so the gradient of that is just going to be 3, 4, no matter where you are, right? So that pink vector is the gradient. If I draw in the gradient of g at our point of interest, I get this. You can calculate them, it's not difficult. Now, what do you notice between this and this? Well, it's a multiple of each other. Grad f is just 5 on 2 times grad g. What's the 5 on 2? Oh, it's one of the lambdas. Ah. Now there's another point down here. If you draw in, grad f is going to point the same way, right? I haven't quite, drawn it to scale. At this point, grad g points the other way. And in fact, the sort of scalar multiple that links those is minus 5 on 2. So that's where that's the significance of that minus 5 on 2. Okay? So the important thing, at each of the points that we've calculated, grad f is a scalar multiple of grad g. And the scalar multiple is known as the Lagrange multiplier. Okay. Now, the next one's a bit heavy, I've got to say. I'm actually going to do something a little simpler than that. I'm going to look at this one. If we have time, maybe even in tomorrow's lecture, we may get back to that one. But that's a pretty horrendous example. This is something a little bit more likely that you'll be tested on. Determine the point on the following surface, or I guess points, that are closest to the origin. And in particular, the points that have positive values. I guess the components are positive. Okay, so we've got our constraint equation. We can form it from there. But what's our function that we want to, in this case? We want points that are closest to the origin. So we want to minimize a particular function. So can anyone suggest what our f might be for this example? What's the actual function that we want to, the nature of the function that we want to minimize? Oh, no, almost. Sphere, right. Okay. Now, technically speaking, if you want to measure distance, you usually have, square root signs and things like this. So, but we also want to simplify the calculations, because let me tell you, the calculations in these problems can get horrendous. So we want to keep it simple. So let's actually write out. We wish to minimize, say, this distance function subject to the constraint xyz minus 1 equals 0. Now, you could proceed that way and not have a problem. However, it makes more sense to be a little bit more careful and more simple, I guess, with this distance function. Who said the sphere before? Somebody mentioned the sphere, yeah. So what I can do is actually, rather than minimizing the d function, I can get rid of the square root, just minimize x squared plus y squared plus z squared, right? I think that's what you're thinking. So it saves us playing around with square roots when we're calculating derivatives. So it's a good idea. So let's introduce a new function, say s, which is just the square of the distance. So there's our constraint, and there's our function that we want to minimize. Okay, so let's formula the Lagrangian, calculate its critical points. Yes. So let the Lagrangian function, it be in this case s minus lambda g, which is just going to be x squared plus y squared plus z squared minus lambda, all times xyz or xyz minus 1. All right, we calculate the critical points of L by taking the partials and setting them equal to 0. So let's take the partial derivative. 2x minus lambda yz. L sub y is going to be 2y minus lambda xz. And L sub z is going to be 2z minus lambda xy. And don't forget, we've got our constraint equation as well. Okay, so let's just put some labels on these because I might refer back to them later. So now the question is, how do you solve these set of equations? And this really, this is a student's worst nightmare, really. You get to this part in the exam, you know the equations you have to solve, and they just won't fall out for you. Now, the other slightly worrying thing is that there's no hard and fast rules on how to solve these equations. Okay? There's a few little techniques and a few little tricks here and there, but there's no universal method. Okay? So this is what frustrates a lot of students. So can anyone see a way of how we might solve these? Any ideas? Yes. That may work. I don't think it's the simplest way. Yes.
Set up a matrix equation.
Oh, that's not a bad idea as well. But no, again, there's a simpler way to do it. Let me. Oh yes. Oh, now you're talking. Okay, what would you do with the second equation? Yeah, what about the third equation? Ah, very good. There's more than one way of doing these problems, of course, but let me give you this is the time to give you the little technique. See here, this is almost the same as this and this. What's the difference between them? Well, if I have an x here, a y here, and a z here, all of these three terms will be the same. So I can multiply the first equation, a, by x, the second equation, b, by y, and the third equation, c, by z. And then I'm going to be able to get a lot of cancellation. Okay? So I'm going to multiply this equation by x. And I get the following. Now, x is positive, y is positive, z is positive. So it's not like, we're multiplying by 0 or something like this. Okay, so let's multiply the second equation all by y. And the third equation by z. So, okay, we've got three equations over here. Now what? Huh? Well, yes, but let's look at it. If I just rearrange these, I can get rid of the lambda x, y, z and sort of just compare. I know x squared equals y squared equals z squared from those equations, right? Just from getting rid of now, x squared equals y squared equals z squared. Let's think about that for a second. If x and y and z are all positive, what does that tell you about the relationship between x, y, and z? Right, x and y and z are all the same thing because you don't have to worry about negatives or anything like that because We're told that all of these bits are positive. So now what? Well, what equation haven't I used yet? This one, my constraint equation. I've used all of these three and come up with something, but I haven't touched that. So what I can do now is sub back into here, say for, get rid of the y and z, I'll get x cubed minus 1 equals 0. So what's the solution to that? X equals 1. It's positive, so it agrees with the information. So, that now is my point of interest. But can you see how, if you didn't multiply A, B, and C by x, y, and z respectively, I'm not sure how you would solve this problem. Okay, you might be able to do it. I certainly would do it the way I've shown you. So that's a good technique because it works with quite a few other problems from Lagrange multipliers. Multiply each equation by a different variable. Okay, it's gold. It's gold. Okay, so let's identify our point of interest. All right, so we've determined the point on the surface, that the points, there's only one of them, that have positive, components, and they lie closest to the origin. But let's actually calculate the distance anyway. So it's not going to be S, it's going to be D. Now, how do I know it's the minimum distance? Why isn't it a maximum distance? How do I know? I'm not performing a second derivative test here. How do I know it's a minimum distance? Anyone got any ideas about that? There's a few reasons. Okay? Firstly, I can always choose a point on this surface that lies further away from the origin than √3 units. Okay, I can just think up various values. Secondly, can anybody tell me why can't this problem have a maximum? Why can't it lead to a maximum distance? Okay, so I've got x squared plus y squared plus z squared. Now, unless I can control the inputs, the x, y, and z, that function will never have a maximum. Okay, this function will never have a maximum unless I control x, y, and z. It'll have a minimum. What's the minimum value of this? 0, right. Right, so unless I somehow control the inputs, I can look at problems where the problem might have a minimum but no maximum, or vice versa. Now let's see how like from our constraint equation, sometimes we have a control on the inputs. So if we look at this, I can just rearrange this to say z equals 1 on xy and then plug it in there. I get a function of two variables, which I've sort of just put into Maple. Now, I can plot some of the level curves of that sort of new boiled down function. So here are the level curves. The yellow means that I guess if you drew them as contour curves, you're sort of increasing. Okay, so the red's sort of closer to the xy plane, and you'd sort of pull these up. So you can see if I move away from the origin, the surface is going up, right? So if I move any direction sort of here, the surface is always going up. Now if I zoom in on this bit a little bit more, here's one I created earlier, you'll also see that if I go into the origin, the surface is going up as well, off to positive infinity. Okay, why is that so? Well, think about the function. As either x or y gets large and positive, this is going to get large and positive, this is going to get small. If x and y get small, this is going to get small, but this is going to get large and positive. Okay? So you would think that if we're just working for all positive x and all positive y, that function can't have a maximum. It might have a minimum, maybe somewhere in there, but it's not going to have a maximum. Just in the last few minutes, I want to really show you why it works. A lot of students get taught this method and they just, oh yeah, okay, it's a pretty method. As long as I can solve the equations, great. But why does it work? Okay? So the real question is, why is there a lambda such that grad f equals lambda g? And basically it comes down to in a region whose interior contains some sort of smooth curve, and you can parameterize the smooth curve. Now, this g here has nothing to do with the g there, all right? So don't mix that up. If P0 is a point on this curve C, where f has a local max or min relative to all the other points on the curve, then grad f is orthogonal to the curve at the point P0. In other words, the vector grad f is normal to the curve. So I'm just going to sort of draw this in sort of two pictures. Okay, so suppose there's some sort of region, and here's my curve C. Now, let's say at this point P0, f has a local max or minimum relative to all the other points on the curve. So we can parameterize the curve. And I'm going to say f has a local max. Now, if we have a local max or a local min, and I've got this parameterization going for functions of one variable, t, what's the derivative going to be at a local max or a local min point? Derivative's going to be 0, right? So the derivative, yes, of f okay, so that's an f here. Now, on the left-hand side, what can I use? I can use the chain rule and get the following. So what does this bottom line say? It says that if this is, say, r and say this is the tangent vector, I've got a right angle. Now we looked at that in section 2 a little bit, so it's now coming back to us, hopefully, that this is quite useful for other sections as well. Okay, so this is a little bit, a sort of a rough sketch of the proof of this idea. But why does the Lagrange method work? Well, I'll just turn the page. I'll come back to this in a second. Now, suppose my f and my g are differentiable. And in this case, P naught is a point on the surface. So in this context, imagine this surface is just the surface G equals 0. Okay? And everything's pretty much the same as before. Now, if I have a surface G equals 0, how can I form a normal vector to the surface G equals 0? What do I do to G? Take the gradient, right? The gradient will give you a vector that is normal to the surface. Now, if f has a local max or min relative to all other values on the surface, well, I can, it's got to have a relative max or min to all other lines that go through the point here. Okay, so I can just draw as many lines as I want. So that means, from this theorem, grad f is going to be also normal to this surface. So if grad f's normal to the surface and grad g's normal to the surface, they've got to be a multiple of each other. They might not point the same way. In my picture, they're pointing the same way. They might point different ways. Okay? So So there must exist a lambda such that grad f equals grad g. Okay, so that's an informal proof of why it works, why there is a lambda such that grad f equals lambda grad g. Okay, it's not a real formal proof, but hopefully you get the idea. You can just really, at least in my mind, draw a picture. Draw a picture to just verify it. Now, great mathematicians and scientists here. Who's the guy on the right? Frink, Professor Frink. On the left, we have Joseph Lagrange. Now, Lagrange was a great mathematician, and I think he probably worked in other areas. You know you're doing pretty well when you get your face on a stamp